right, well, bonjour, ladies and gentlemen, mesdames et messieurs. Je m'appelle Doug Howarth, and I just about ran out of my French right there. Désolé. Thank you for coming today. This is a story. This little presentation I have here is a story that dates back several hundred years. In fact, to this gentleman right here, René Descartes. About 400 years ago, Monsieur Descartes was lying in a bed, the story goes, and he saw a fly buzzing along, and it landed on the ceiling of his flat. He was looking at it, and he was trying to describe where it was in space. And to that date, nobody had come up with a way to describe where something was in space. And so he invented what we now know to be a two-dimensional Cartesian coordinate system. Lucky for him, it was named for that, right? And then the 3D Cartesian coordinate system. So this is back in the 1600s. So fast forward 350 years, and a young junior high student was studying it. That was me. And I saw this 3D system, and I said, I wonder if there's anything else to this. So this was something that was sitting in the back of my mind for decades. And the one day I went out with my wife, and we're buying a washing machine. And my wife says, I like this machine. It's got more cycles than we have at home. And I go, cycles, that's an integer, and I can plot that. She says, it's also got more capacity than we have at home. I thought capacity, we can plot that too. You know, the capacity goes up. And she says, it's also got a pedestal on it. So I go, well, that's a step function that actually had a step in it. And then I said to her, and then I asked, I said, well, what about the next model up? Because they had another one that was the same brand. And she says, well, we can't afford that. And I realized at that instant that she was juggling 4 dimensions in her head simultaneously. And so I ran off and had this epiphany, which is you're going to see here as a 4D model. And then fast forward another 10 years after I made the company and started to do some work in the field,
I was working with this American aircraft manufacturer, and they were working with a European manufacturer. The company I was working for wanted to try and sell a new jet trainer to the United States. They were working with another company, an engine manufacturer that didn't want to drop their price. And we had to drop the price to win. Another company ended up winning.
So I got to wondering if there's a way to model that. Now, I know a lot of you are in tiers below the engine manufacturer, but the same principles that apply to an OEM and the engine manufacturer apply to the engine manufacturer and all the pieces that go into it and all the pieces that go into the plane. So this is actually very applicable to what you do. This actually shows the geometry that's involved in trying to figure out how to make more money for your employers, or in this case, if you own your own company, for your own company. So with that in mind, let me tell you a little bit about what we're going to talk about today. And so we're going to talk about this new phrase that we have here, hypernomics. We're going to talk about extending what René Descartes did. We're going to talk about the twins. So my wife helped me figure out the 4-dimensional problem. I'm going to have my daughter here. She's going to play 2 parts. She's going to play the twins, and she's going to help us figure out how to create a 7D system. So she's going to be in that. And then we're going to talk about pole position, and this is not your F1 pole position. It's a different pole position. And then we've got some funny math here. We've got 3 + 2 = 4. What does that mean, Doug? Well, we'll see. We're going to talk 4 + 4 = 7. You're out of your mind, Doug. What does that mean? We'll see.
That's what we had to do for...
And then we're going to have a 7D trade. That's what we had to do for...
that aircraft manufacturer.
And then we're going to add time to this. And happily, we have back to some normal arithmetic. 7 + 1 = 8. And then we're going to sum all the stuff up and show you what you can do with this. And there's also some interactive stuff we can do if we have a little bit of time. So for example, a lot of you make parts that if they were lighter, add more value to your OEM. And we can show you how you can model that. That's part of what we do. So with that in mind, what is this new phrase that I came up with? Well, it's a class of phenomena that we couldn't see before. So if you go to the dictionary, and I did, hyper can mean existing in more than 3 dimensions, hyperspace. Now these are mathematical dimensions. So these models you see here, these are 4-dimensional models. In this case, this is for the fighter bomber attack aircraft in a certain period of time, and this is for the stock market. So we're actually using this for stocks right now too. And that anonymy means it's a science or a group of laws describing a new topic. So hypernomics is the study in 4 more dimensions of this new field. So what do we do with that? And who's involved? Well, you've got me. And so as I said, I found this, listening to my wife, listen to your spouse. She or he may know something you didn't know. I paid particular attention to mine, and I often tell her to give the presentations because it's her idea, and she always says, don't tell me about that. It is patented. I have now 15 papers across 4 continents that we've talked about this. I've been to the Royal Aeronautical Society 4 times, talked out of South America and Europe, Australia. For those of you who have heard of it, I worked on the stealth fighter for a while, was the program manager for the manufacturing line. And I've got this degree in economics, and one of my problems was I never believed what it was I was studying. It turned out they were all wrong, and you're going to see why they were all wrong, and you can see how we can substitute what they are trying to tell you as the truth for something that's a lot closer to the truth. Rich Marino is Will's good former friend and employer. He's our COO. Ken, he did, yes. Ken Joris is a longtime friend and a brilliant engineer. He and Shad Torgerson wrote most of the code for the software that you're going to see here in a bit. That's all in your package, so I won't walk through every line here. And then we have some pretty interesting contractors here. Anybody heard of the F-35, the vertical plane? Well, my good friend Dr. Paul Bevilacqua, basically invented that lift fan in a flash of brilliance. He said in the shower one day, in 5 minutes he went from nothing to figuring it out, much like I came up with the 4D system. And for that, he won the Daniel Guggenheim Award, which is basically the aerospace equivalent of the Nobel Prize. Past winners include Oliver White, Charles Lindbergh, Jimmy Doolittle. And then we also have Dan Raymer, occasionally contracts for us. He's written the most popular book in the world on aeronautics. And so he's a pretty useful guy to us. So who's used? Who are clients here? These are some of our clients. We are just starting with Over Air, which is one of the entrants in the urban air mobility market, also known as electric helicopters. And you can see these other outfits for whom we worked. So we talked about extending Descartes. And what does that mean? Well, I'm trying to remember. Corentin, you went to Lycée Descartes? See? Did you? You went to Descartes High? Your bio says you did. Did you not? Did you go to Descartes High School? Okay, so you probably heard a little bit about René Descartes, right? Sorry, I read up about it. I did dossiers on everybody here. Sorry. That's what modern people do, right? They dig into what's going on here. Yeah, there's a little side note. I was recruited by the CIA when I was out of college, and I didn't go to it. But that little bit of CIA interaction kind of got me into this bit. So René Descartes, as I said, worked out this 2D system, which looked a lot like this. This 2D system, all the red zones have negative numbers to it. And that one zone listed as number 1 doesn't have negative numbers associated with it. And then he's got this 3D coordinate system, X, Y, Z, and for where we are here, latitude, longitude, altitude, that's a 3D system. What's interesting, though, is in business, you can have positive costs and you can have positive revenues, and costs can be more than revenues, and you're saying you're in a negative position. But each one of those positions isn't really negative. It's the relationship of one number to another. And so the insight that I had was that I asked myself this question based on what my wife was doing, which is, what can we do if we had a coordinate system that didn't have negative regions? And also all without right angles. So it turns out we can make even more dimensions here if we want to keep playing with them. But we're going to just get up to 8 today. I think that ought to be enough for today's discussion. So in order to help us out here, I've enlisted my daughter. She's playing some twins here. There's going to be Christina. Christina is an American expatriate in this story. She's living in Argentina. She studies development costs, quantities and price relationships, business jets. They're both studying business jets, turbofan engines.
Hola, amigos.
She wanted to say hi, so she just did. Okay. Meanwhile, Sheila, her twin, she's an American expat living in Australia, and she has her own list of studies that she has. She studies much the same thing, but in a different part of the market.
Good day, mates.
So the twins are going to study these forces here and see if we can kind of describe how the market assembles itself. Now, the one thing that I want you to understand out of this, another major finding is that markets self-organize. They form their own limits. So, for example, here, this is a hard limit on this 4D model here. This is a hard limit. This line right here is a demand frontier for the fighter, bomber, attack aircraft market. That is a very stable line. This line has been roughly in the same place. It's changed by 2% in 25 years. So the people form boundaries for themselves, and then they reward products largely in the same way. Just like we know there's nobody going to come through the door that's going to be 8 feet tall or 2 feet tall. We know that the height of all the people is gathered between, say, 4'6" and 6 foot and 6'6". That's going to describe 90% of the people we're going to see, or 95%. Using that same technology, we can find out how people reward features, like with a battery, what the weight would be versus the amp hours, things like that. In school, I was taught, anybody here take an economics course? Show of hands, nods, yes. Paul Samuelson won the Nobel Prize, and he said that there was only one equilibrium point in a market. So in this case, you're looking at this horizontal axis is the amount of iron ore that's being produced worldwide, and each one of these bars is a different mine. And so the lowest cost mine is the one that's furthest to the left, and as they go this way, they get more and more expensive. And so if you put a green line above that, so they have a profit margin. There's a supply curve there in green, and there's some sort of demand, and then where those two things intersect, that's supposed to be equilibrium. And so Samuelson said there's equilibrium in every market. Well, the twins decided they want to take a look at this and say, is that true? Well, let's take a look, the girls said, because planes use iron. So they looked at how the aircraft market began, and it began with a single sale of a single model, the Wright Flyer back here. And so there's one point here, and Samuelson would say, we've got equilibrium again, 1 point. But just a few months later, there was a second plane. And all of a sudden, there's no equilibrium point.
No bueno.
Or
Crikey.
I think in French, this is mon Dieu, right? This isn't what's happening. So this is reason enough. If you know just this, you can say that Paul Samuelson was completely wrong. That is enough to prove him wrong right there. So proving him wrong is one thing. Putting a substitute in for what we should see is another. So that's what we're going to get into, is how do we go around this and see what can we do to prove out how markets actually work in the real world. Now, you're seeing some business jets here. Will, thanks for dropping all these business jets in. That becomes a great backdrop to what we're doing here. So Christina decides to study the business aircraft market. And what she does here, She's plotting all the vehicles that have been business jet demand. There's actually turboprops in brown, business jets in blue, and she's plotting all the planes that have sold over the course of 10 years here. So for example, there's the Global 6000, the G650. Way up at the top, those are the airliners that are converted into business jets, the 747, 77, et cetera. And here are some turboprops. And so what you see here is there's an upper frontier, an upper boundary. That's the most the market can handle with respect to price. And then there's an outer boundary, what happens when the markets get saturated. So for example, this PC-12 is actually worth more, according to our model, than what it's paid, than what they're selling it for. So what they did is they lowered the price, and they went from being limited by price to being limited by quantity. So that's one of the things that this kind of an analytics can do for you. So for example, with your batteries, you could plot this for your batteries and see what the battery limits would be. Since your company's brand new, the frontier for the market's way out here, and you're building batteries down in this range here. So she decides to extend her analysis into the engines that power up these business aircraft. These are specifically the jet engines. And you see this has got a nice boundary too. And so her sister says, well, that's pretty good. So now her sister's Sheila is going to get in to look out to see what supports the business aircraft prices. And so what you're seeing here is you can actually have a pretty good idea there. That's a large Dassault. It's got a lot of cabin volume. And it's got a high speed. As you go over here, this plane is smaller, it goes slower. That's almost the same speed, but it's smaller. And so what happens here is there is a relationship, this surface here, that describes what the planes are worth based on their speed and their cabin volume. Now, if you're below that surface, as shown here, if you're below the surface, you may be underpriced. If you're above the surface, you may be overpriced. And so if you make adjustment, or there may be other variables or features that are involved there, but if you adjust those features, you may be able to make more money. That's the whole objective of this, is to not leave money on the table. And this first cut has turboprops in it, and it's this number. The closer the R square is to 100%, the better it is. If we take the turboprops out and just look at jets, you get a different surface. You see how this changed? This is all the jets that are part of that, less the turboprops. Different surface. And it shows that there's a tighter correlation here. So this ends up being useful for us to be able to minimize the error that we're going to talk about here. So Sheila goes off and studies the turbofans as well, and she looks just at the jets. And basically she's saying the more thrust you have and the lower the SFC is, the more the return. So you see this has got a surface that's different than the other one that you just saw. The price rises as the SFC falls. And so if you could do something that would improve the SFC of an engine, say, for example, if you made a fan blade, that would be helpful. So her sister likes that. The breakthroughs, as it is here, is that these analyses they're related. And so the twins want to view these things side by side. So we've got an Australian twin and an Argentinian twin. And of course, nobody's got a border with Australia. What are you going to do? You can't. These girls used to live in two rooms, the story would go, that are joined to each other. Now they want to replicate that, but they can't because their countries are separated. But what they do have is they've got territories that they claim in Antarctica. So is France. You see, France has got a little sliver there. Here. They got territories that they can claim in Antarctica. And so they say, well, if we went to Antarctica, what would it look like? Well, we could go down to the South Pole. The United States has a facility there in Brown, and the South Pole is there, and those are the cuts of land that each country claims for itself. And there's actually a South Pole marker there. And if you came back to that first slide, you'd see the flags of all these countries are around that. That was the South Pole in the beginning there. So the girls say, well, what would happen if we took our analyses down to the South Pole? So the twin that's studying demand has got quantity and price. So she's got dimensions 1 and 2. And the twin that's studying cabin volume, that's studying the value, has got cabin volume and speed and price. And they say, oh, we got them. They're very nice. In fact, they're so nice, they're similar. They're similar in the sense that the vertical axis for the demand curve, 1 and 2, is price. And the vertical axis for this value space is price. So they say, because of that, we can take these two systems and join them. So they take this 2D system here, far picture, the 3D system, and they just merge them onto the South Pole. So now the common axis is the South Pole. And so now they have this 4D system, and it looks like it's bound by the land, but in reality, so this is where we get the funny math. This is those 3 dimensions, and those 2 dimensions equal the 4 dimensions here. So 3 plus 2 equals 4. What we discover is that those systems don't need to be tied to a physical dimension. So this is a 4D system. It's a 4D system like this. It's a 4D system like this. It's a 4D system like this. It's not bound to traditional lat long elevation kind of characteristics. And this turns out to be pretty important. That's what we're going to study here going forward. When they plot their value analyses next to their demand analyses, they find that they're entangled. Now what that means is that every point on the left, the speed, the cabin volume, and the price, is tied to the demand for it, the price, and the quantity for each one of the vehicles. Now this entanglement turns out to be massively important because you can make something more valuable. If you make something more valuable going up this way, if you make it more valuable going this way over here in the green, you're going to be putting the price up, you're going to reduce the number that you're going to sell. And that's something that we want to study here. So everything has what's known as an ordered quad. And this reveals what we call the law of value demand as opposed to supply and demand, which is basically that the features of a product determine its value. So again, with these planes, the cabin volume and the speed determine the price of that to sell, or the value of the sell. The value determines the price. The price in turn determines the quantity sold, and quantity sold is one of the features of the system. So if you sell enough, you're going to have to drop the price down. So here's an example. So here's that same system without all the lines in it. And we're going to examine the Boeing 787 business jet. So the features of the 787 are that it's got over 16,000 cubic feet of volume in it. It's got this speed. And those two features combine to determine its value. Then that value in turn sets the price. So that goes up here and it sets the price. $250 million. Now that price, as it turns out, then sets the quantity that limits the number of sales that they have. And so that comes out here, it runs into this yellow line, which is the demand frontier. And so they can sell 12 over the course of a decade. Now this ends up being massively important because we're going to talk about how their limits react with the engine limits. And you can imagine this happens with every component in every plane all the time. In fact, in every system. So they do the same thing for turbofans. They plot them together. And they realize that their entangled too. So again, all the thrust and the SFC determines the value determines the price determines the quantity sold. And so these things are intermeshed. Always have been intermeshed. You've never been told they've been intermeshed. They're entangled. This is the way it's been for forever. Everything you've been taught was wrong. This is exactly what's going to happen. In fact, I went to the Air Force and told them, based on this model right here, they tried to say that they're going to make 100 B-21 bombers, and that was way past this line here. I said, there's a chance you're going to do that. That chance is less than 1 in a million. And so what we're going to see here is I took this analysis, and there's a company that was entering the business aircraft market. I say was, because we're going to see what happened there, called Arion. Arion was a little company that was backed by Robert Bass. He's a billionaire from Texas, down south from in here. And he got together a fine team. He got some Airbus people. Airbus wisely got out. He got Lockheed in there. Lockheed got out. But he was trying to build a supersonic business jet. Wanted to go 925 miles an hour. And they set a price, and it was worth every penny. And we're going to see here what happens when you do that. But they had a problem with demand. What turns out, what happens here, and basically what I'm doing, is I took the 1,4-D system and put the other 4D system right behind it. So on the front, you see these are engines. You saw that from before. That's their value surface. And behind there, you've got the quantity. Basically, what I'm doing is I'm taking two 4D systems and I'm putting them back to back. So 4 dimensions here, 4 dimensions here, but they share the price axis. So 4 plus 4 now, some new funny math. 4 plus 4 equals 7 when it comes to dimensions. So what can we do with this, Doug? It looks like you're just doing a lot of geometry that I can't understand, that I don't see what's going to happen. Well, what happens here is any new engine's got to go into, so here's a new engine, that green ball here, it's got to go into a new vehicle. And so these two things are intermeshed. They're entangled.
Again, what happened when I was working for one of my clients, we asked their supplier to drop their engine price.
If one doesn't drop it, then you're not going to be able to drop the entire price. What does that mean in practice? Well, let's take a look. So here's a 7D trade that could happen for the Boeing BBJ. So if you've got lots and lots of money, I think Florence said she worked for an outfitter for the cabins, didn't you, Florence? For business jets? Well, the 787 has been made into a business jet 12 times in the course of a decade. So let's consider where it is. So we're going to use just two of the dimensions here. The 787 is right now at 12 units, that upper blue dot, at $250 million. Now they're really close to this blue line here is their demand frontier. And so suppose they wanted to sell 20 of them. They want to get down to 20. Well, they have two engines. They use a GE Gen X engine. And that engine is right up against its demand frontier. So it works out that if Boeing wants to sell more aircraft, they're going to have to drop their price from 215 to 194. And GE is going to have to drop their price from 27 to 23.5. Now, meanwhile, this is very important, the cost for both these vehicles, both these products is here. So here's the cost in blue for the BBJ is that lower line. So if you're bringing the price down, but you're still above what your cost line is, you're making more money. So in this case, Boeing came down from 215 to 194. They're still making money because they're above the solid blue line. GE has come down from 27 to 23, and they're still above their learning curve. They both made more money by dropping the price. So you have to understand your cost and what the thing is worth. In this case, about 25% of the cost of the business jet is wrapped up in the engines. So it's a pretty massive thing. If you want to drop your price significantly, you're going to have to get all your subs, and most of you work in the subs community, you have to drop the price there. I was saying that I studied the business jet here, which is the Ariane AS2. It looks like this, or wanted to look like this. That's a rendering. Now, I worked out its cost. There's a way to work out development cost. And so that line there represents the development cost for other business aircraft. These are all going subsonic speeds. So the AS2 was above that line, which means it was probably fairly priced. And if you do a little bit of work, and that we don't need to go through that in detail, but it basically shows you that it was worth, that's probably a good cost estimate. But we need to calculate the value of this. And so we used one of these equations here that we showed you before. We take its cabin volume and its speed, and it comes up and it hits that surface. And it says it's worth 160 million bucks. Now, they were selling them for 120. So, you know, they weren't overpriced. So, but there's a problem, because they hadn't finished the analysis. And that problem is that, well, first of all, this is an extrapolation, but what about demand? That's the one thing we want to ask ourselves. What happens with the demand curve here? And so what we're going to think about is how markets move over time. I think the easiest way to look at this is that these markets have a limit that can move quickly or slowly. So in this case here, you can imagine a soccer ball moving forward in time. So there's a soccer ball here, it moves here, it moves here, and it moves here. And so it's moving through space over time. Well, markets move in space over time. And some move hardly at all, and some move pretty quickly, and some are in between. So we're going to see 3 examples of this right now. So in the market for fighter attack bomber aircraft right here, which is this guy, this line right here has moved about 2% in 25 years. It's not moving very much. It's effectively at rest. And so what this means is that 25 years ago, you see that B-2 target up there, somebody tried to, well, somebody being Northrop, wanted to make 132 of these vehicles for a certain price. And because it was too high priced, they ended up only selling 21 of these vehicles. Back there, they went to the actual. So this turns out to be massively important for that market. Now, what happens in other markets is that it changes pretty quickly. So again, we're going to switch over here now to electric cars. Most of us are in aerospace, but this is useful information, especially if you make batteries. So the electric car market began in July of 2009. There was a single Mitsubishi i-MiEV built then, and it sold. So as soon as that happened, that one point there represents the single sale for a single unit in that year. And as time marched on in that year, the quantity started to increase. Notice this log scaling here, until they had a certain quantity out here. And then as time went by, 3 years again, another 3 years, and another 3 years after that, and yet another 3 years, this frontier is starting to change pretty rapidly.
If we explore the electric helicopter market, that market is going to move like the electric car market.
I'm convinced of that. We have to verify that, but that market is moving very fast. And so you want to figure out, if you're moving in that market, what can you do to help support them? But let's go back to Ariane. In December of 2020, having studied Ariane, I told those people that they didn't have a chance of making their demand target. They wanted to sell 300 of these vehicles, and they ended up having 20 firm orders. So in 2004 through 13, if you plotted the demand frontier, you get that yellow line. So they started around 2009. They had these 20 firm orders. They wanted to hit 300. The business plan was based on that. And then 5 years forward, the market moved slowly, and they still had 20 firm orders. So the eighth dimension here, 7 plus 1 equals 8, the light blue up there, we're going from 5 years before to 5 years ahead, and these are in 10-year increments. So it's kind of like that soccer ball has moved half a soccer ball width. That's what we're capturing here. And so I wrote him a note on LinkedIn and said, you're not going to make it. And I had a guy that I used to work with at Lockheed Martin wrote an angry reply. Well, we just got a whole bunch of orders. You're wrong. I go, good for you, got orders. You're still not going to make it. And they went bankrupt in September of last year. You did? Yeah, I know. It was one of Will's clients. But it proved out the math. That's kind of what we're trying to do here. So there's other ways to prove out the math, and this is another way to make the idea a little bit easier to understand. So if you look at here, this is over 10 years, this is the number of business aircraft sold, and this is the number, again, remember their price was 120 million. They wanted to sell 300 in a decade. So the number that's greater than 80 million, not 120 million, 80 million was just 55. And the number from 60 to 80 was 20 times that. So that tells them you're not going to be able to build it. And then you can do another analysis, which I did here. Concorde. Anybody familiar with that? Aerospace, French? Yes. Oui? No? Yes? They did the same thing. They didn't do their analytics was based on projections from people say they're going to buy it, but they didn't look what actually people have bought. And so one of the important things that comes out of this is you don't listen to what people tell you. You see what they've done. So you take the past behavior, the current behavior, and then project the future behavior. Past, current helps give you a projection for the future. It won't be perfect, but at least you've had real data behind what's happened, what's happening, and what you propose is going to happen. So Concorde, over here on the left, they wanted to have 350 sales. Firms plus option, they had 100. They sold 20. And Ariane wanted to sell as many as 500. They claimed that they had up to 93. Firm and options, they had 20. Firm, as near as I can tell, they didn't sell one. They didn't finish it. There's no magic to this. It's just what happens here. Another thing that comes out of this is that the demand frontier, they thought that they were making a brand new product. And it turns out they're just making another aircraft that's going faster. Now, these electric helicopters are a new product because you're making the sound so low that you're actually making something different. But what we did here was we're looking at cars, electric cars and gas cars. So the gas cars are in this light blue here, and the electric cars are in green. And what you can see here is that the supersonic people were trying to argue that this is a brand new thing that was going to create its own demand curve. But when you plot gas cars and electric cars, you'll find out this is the demand frontier for gas cars, and you'll find out the electric cars here in green are abiding by the same frontier. So this is something we have to take into account. So in sum, this is economic entanglement. You've heard of entanglement in physics. Turns out that this stuff is entangled. So the value entangles with demand. The markets entangle with each other. So the engines go into the planes. The fan blades go into the engines. The batteries go into the aircraft. The springs. The composite parts. They're all parts that go into a bigger plane. Your prices are somebody else's costs. And you can actually see how these things interact with one another. And what we discovered with the Boeing 787 is a lot of times you're not going to be able to sell anymore without some concession from your major suppliers. And then if you look at time-phased market snapshots, so I was taking a 10-year snapshot here and another 10-year snapshot that went 5 years ahead, it's kind of like looking at a soccer ball that's gone from one diameter to half a diameter ahead. So yesterday and today entangle with tomorrow. You're kind of bound by that. And I'm going to give this to a cost group, and what I'm trying to tell them is just having a good cost isn't enough. And broad estimates should take into account all of that. So with that,
Adios, amigos. Okay, no worries. Bye, mates.
the twins thank you, and I thank you.